what's useful and so like that's what we're going to you just like look at the question and stare at it. Yeah, it was I'm like, why would you he's like, after he went out, he's like, you'll learn something in the test. You'll learn something. It's just like, that's not what a test is for. That's what they teach you. Test is a what? Test is learning in the test.
Actually, one of our other professors said that too. I think it was science, right? And you're supposed to learn something while you're taking the test.
Yeah, that's why he's always higher because he's doing something new.
Well, then like the transport final last year was like you have to learn the entire section of the book and answer the question. That was actually
like he has two questions about like
stuff
itself. We covered one.
no, we didn't. We barely covered it, but you had to read the book. It was in the book. There was an entire section, so I just wrote down the equation, got like all the points, so like just started writing down the equation in the book.
Yeah, they're pretty good.
Score was like grading. I didn't give a shit. Yeah.
What do you mean?
Yeah, but I'm using
Yeah, that's what that is. What?
That's like all the labs. Oh, yeah, they made it first two laboratories.
Fall back to
Moan and moan, and they realized, oh, okay, maybe we were pushing it.
taking it off either. They had gone through Well, they switched it up more, so like the first half of the semester, it's like a conjugate, 6 weeks. It was like,
Oh, I see what you
then with thermodynamics, they did the same thing, like Sarkar and Saxon, but they was like half the semester was Sarkar.
I appreciated that a lot more than Ogle and Sax.
Ogle and Saxon makes sense.
Ogle and Sax.
it's like a completely different class.
And then all the tests and stuff were like heavily Ogles, like if I remember correctly. It's like, okay, so let's spend one day of the week on that, where there's like more to do. Stuff that, well, I all one. It was, I don't know. It's like the first part of the semester is like,
And then like didn't know what the course was about, like halfway through the semester, you just started asking everyone like what is the course again?
and then you talk about the grid.
And then he's like, oh, I just started recommending things to you, like I don't even know what's in it, like what was the whole board portion. Sophia was telling me about it.
I write more in lab, the controls lab than I did. I've already read
Sophia, pretty much everyone in lab.
Okay, good morning everyone. So I have handed out your midterm exams. If you have any concerns that you might get more points, by all means, let me know. Just send me an email or give me your exam book and tell me in which problem you should get more points. Okay, let's see. So, any questions before we start? Yes?
So I just have one question. Homework that we submitted.
That you submitted today. Okay, go ahead.
So
Which?
problem number 5, I think. It's the big tabular column one.
Okay, let me just try to go to the website and then we can take a look. Okay, you are asking about problem 5?
Yes.
Okay.
I think it's number 11. It's the fifth one from the bottom.
Okay. So what do you want to talk about?
So,
Are you talking about this A0,
the one before it, Professor.
the one above?
Yes.
A, B, C, D, E, F, followed by A, B, C, D, E, F. Okay?
That is almost like a multiple copy of the first one, right?
Yes, exactly. So the first one is the DFT of the DFT, and then this is 2 copies of that.
So when I do it, what would the scaling factor be? I'm getting a 2 times increase when I do it with MATLAB. So this one.
You are getting 2 times increase by MATLAB. Huh. That shouldn't be. I mean, that really shouldn't be. So I guess the more important question is what happens to the scale factor if you just take 2 copies in the time domain. So, that's a good thing to start with. So, okay, so let's see. We talked about that before, how to think about copies in the time domain. So if we have, let's take n is equal to, okay, in this one 6, but let's take 4. So if I take 4, A, B, C, D, whose DFT is A, B, C, D. Okay. Then what do you expect if you take 2 copies, A, B, C, D, A, B, C, D, and you would expect some constant k times A, 0, B, 0, C, 0, D, 0. Okay. And so, any questions so far? Okay. So what is that constant k? Is that 2 or not? Is that 2? So how do you, okay, let's do a quick check. So A squared plus B squared plus C squared plus D squared is equal to 1 by 4 times, well, to be strict, I should take magnitudes, but if I assume them to be real, these are complex conjugates. So by the Parseval property, total energy in the time domain is equal to 1 over n times the total energy in the frequency domain. Okay? So now, what is the total energy of the repeated sequence? That's going to be 2 times A squared plus B squared plus C squared plus D squared. That's the total energy in the time domain. Must equal 1 over n. So this is 8 point DFT. So that's 1 over 8 times some constant k squared times this whole thing. Some constant k squared times all of that. Okay. All right. So now this whole thing here, this whole thing is, if you bring the 4 to this side, is going to be so this whole thing is going to be 4 times A squared plus B squared plus C squared plus D squared. And then that cancels out, 4 cancels out, so K squared, bring the 2 to this side is 4, which means K equal to 2. So I was just trying to, in case you forgot, that should be 2, because I took 2 copies, that K should be 2. Okay, we talked about that before. Is that any helpful to you? Okay, anyway, think more about that. So we should post the solution by sometime by tomorrow, 9 or 10 o'clock. if you have questions, we'll talk more about those in my office hours next week, Monday 3 to 4 o'clock or Tuesday after the class. Any other questions? Okay, so your next homework is posted. I think the class, the pace continued. So the next homework is primarily on chapter 9. I think we are, we have to keep moving. So, so chapter 9, next homework has been posted. That's due from a week from today. So the main idea that we want to talk about today is the fast Fourier transforms. So computing fast computation of DFT, that's by the so-called FFT algorithm. So, and that's known as FFT, fast Fourier transform. So if we have two signals A and B, okay, whose DFT is cap A and cap B, and cap A is going to be A plus B, cap B is going to be A minus B, okay, and that's called the two-point DFT. So if we have A and B, and then A plus B, and then A minus B, is called this type of two-point. This is a two-point DFT, which is also known as a butterfly because it looks like a butterfly. So anytime the two terms that you will hear a lot in FFT is the butterfly and the twiddle, and so we'll talk about that. So anytime we talk about a butterfly unit, that's just computing A plus B and A minus B. So that's what it's computing. Okay. So the whole idea of fast Fourier transform is essentially to do divide and conquer. So if I can take a if I can use a 2-point DFT to compute 4-point DFT, and then use 4-point DFTs to compute 8-point, and then use 8-point to compute 16-point, and so on. So so FFT is considered one of the top 10 algorithms of the previous century. So definitely it's a very important algorithm. So the whole idea of divide and conquer is I'm just curious, how many of you have taken a class like a Computer Science 4041? Very few. Most EE students don't take that, but that's a nice class to take to learn about path algorithms and all kinds of simple algorithms. Very useful. Okay, so our goal then is to solve a problem of size n by solving two smaller problems of each of size n by 2. So if I can express one 256-point FFT as a 128 point, and then each of the 128 point can be expressed as 264 points, each of the 64 can be expressed as 32, and that continues. So that's what is called divide and conquer, and that's the very basic principle of taking a large problem and divide that into smaller problems, and the smaller problems are easier to solve. And we already solved the smallest problem, which is computing the DFT of two samples, A and B. Okay, so the so-called there are two algorithms, two divide and conquer algorithms. One is called Decimation-in-Time, so DIT or Decimation-in-Time algorithm basically says you take the signal and decimate that in time domain. Okay, so what does that mean? So we know that xk is summed over all n equal to 0 to n minus n n minus 1 xn e to the power minus j twice pi over n k n. That's what I want to compute. So what does decimating in time mean? So that means if I have a signal, let's say for a simple example, let's say for a 8-point signal, I have x0, x1, x2, x3, x4, 5. Okay, let's take 6 points. So if I have a 6-point signal and you decimate that, you get x0, x2, x3, x4. And then you decimate that to get the odd parts, and that becomes x1, x3, x5. So these are called the even parts, and these are called the odd parts. So decimation in time suggests that I can write this as two sums, one containing the even parts and one containing the odd parts. So these are two time domain sequences, each of length n by 2, decimated in time. So I can say that this is, let's call some r as an intermediate variable or another variable. So r is equal to n by 2 minus 1. So in this example that I showed here, n is from 0 to 5, r is going to be from 0 to 2. Okay, so r, the possible values of r is half of the possible values of n. N has total 6 possible values in the range 0 to 5. R has half that, 3 possible values 0 to 2. So I can then write this as x2r. So I'm just replacing n by 2r, and that's what we are doing. This is n is equal to 2r, and r is equal to 0, 1 and 2, so n becomes 0, 2 and 4. And here these are the odd samples, n is equal to 2r plus 1, where r takes the value 0 to 2. So this is x2r, just replace n by 2r, the even samples, e to power minus j twice pi over n k, and I'm just replacing n by 2r. That's the even part. For the odd part, so I have the same thing here, r equal to 0 to n by 2 minus 1. And now instead of 2r, I replace n by 2r plus 1. That's an odd sample, e to the power minus j twice pi over n k 2r plus 1. Okay, so this is n replaced by 2r. For this part, n replaced by 2r plus 1. So all n divided into even samples and odd samples. Even samples, n replaced by 2r. Odd samples, n replaced by 2r plus 1. Okay, any questions? Decimation in time. So if you look at the first sum and take that 2 outside of here and remake this n by 2. So if you take the 2 outside the numerator and make that part of the denominator, how many of you recognize this sum here is the n by 2 point DFT of the even samples? So this is r going from 0 to n by 2 minus 1. Think about the size of the FFT as n by 2 minus 1. x2r, these are the x0, x2, x4, whatever those values are. So, and then e to the power minus j 2 pi over the length. Length is now n by 2 k times r. And this is indeed the n by 2 point DFT of the even samples of xn. So we started with an n point, cap n point sequence, divided that into 2 sequences, the even sequence and the odd sequence, even each of length n by 2. And again, remember, we are trying to decompose a problem of size n expressed in terms of the same problem recursively. So here, this is a recursive computation of problem size n by 2. And the first sum is easy to see that. This is simply n by 2 point DFT of the even samples of xn. Now, in order to see that how this can be expressed in terms of n by 2 point DFT of the odd samples, we have to multiply these exponents and write that separately. So we'll get back to that, but let's take the second part and see what happens. Okay, so e to the power minus j twice pi over n k times 2r plus 1 can be written as e to the power minus j twice pi over n k times 2r times e to the power minus j twice pi over n k. So x to the power a plus b is x to the power a times x to the power b. Okay, and then for the first part, I can do the same thing, bring that 2 to the denominator. And so I can then write the whole thing is equal to summed over r equal to 0 to n by 2 minus 1 x to r e to the power minus j twice pi over n by 2 kr plus, now this quantity here e to the power minus j twice pi over n times k does not depend upon the summing index r. So that comes outside the summing index. So plus e to the power minus j twice pi over n k times summed over r equal to 0 to n by 2 minus 1 x 2r plus 1 times e to the power minus j twice pi over n by 2 kr. Okay, so this quantity here is the n by 2 point DFT of x to n or to r, whatever you want to call that. And this here is the n by 2 point DFT of x to r plus 1. So, so if we call these even samples, so let's call them GR, and this call this HR. So GR is the even sample, and this is the odd sample, and then we could call, well, actually I could call them as GN. So let's call this GN, n equal to 0 to 2. Well, okay, R is, it doesn't matter. Some time domain. Okay, so so we can then say this is equal to GK, which is the even sample, DFT. Remember, GK and HK are n by 2 point DFT. So what it says then, if I had a signal xn of length n going to compute, this is xn, computing xk of length n, and now we can decompose that into the even samples x2n or 2r, whatever you want to call that, 2n or 2r doesn't matter, of length n by 2, and compute an n by 2 point, this is n point DFT, this is n by 2 point DFT, and take the odd samples and compute another n by 2 point DFT, and call this GK and call this HK, and then we can replace, we can combine these things, we can merge, we can call that merge, or combine, doesn't matter, and then compute XK, which is the n point DFT. So that's really what is happening. We are computing an n point DFT by first computing two n by 2 point DFTs and then merging them or combining them through that equation right here. Okay. So we are done. I mean, that's kind of the problem is solved. I mean, this is the recursive formulation of expressing an endpoint DFT in terms of 2n by 2 point DFTs. That's essentially a recursive formulation of the problem, divide and conquer problem, and then you can keep doing. So replace this by 2n by 4 point and emerge. Same thing here, 2n by 4 point. Each n by 4 point can be 2n by 8 point and emerge, and process continues until we come back to the simplest one, which is the 2 point, which is the butterfly. Okay, so let's now think about a little about the combination or the merging unit here and what is going on. So the xk is given by this quantity. Now remember that this gk and hk are n by 2 point DFTs. So there is no problem if I am computing k equal to this k, the index of that k is 0 to n minus 1. However, the index of this gk and hk, these indices are 0 to n by 2 minus 1 because these are n by 2 point. So what happens, let's say that cap n is 16, let's say. So up to x0 through x7, I can use this formula here. So for example, x7 is going to be g7 plus e to power minus j twice pi over 8 times 7 times hk. But what is going to be happening at x8, 9, 10, etc.? What does G8, G9 mean? Any volunteers? What is G9? So remember these, although we are talking about DFTs in the back of the mind, the math basically says these are all implicitly periodic with period n by 2. Well, these are n by 2 points, so these are periodic with period n by 2. So G9 is going to be same as G1. Period is 8. So 1 is same as 1 plus 8, 1 plus 16, and 1 minus 8, etc. So for any k greater than or equal to n by 2 up to n minus 1, interpret these as periodic with period n by 2. So for example, G9, x9 is going to be G9, which is same as G1, plus e to power minus j twice pi over n times 9, h9, which is same as h1. So if I want to explicitly write down so for k is equal to n by 2 plus L, where L is 0 to n by 2 minus 1, then xk is going to be gk plus e to the power minus j twice pi over n k hk. Now, because of, so this can then be written as g of so x, so if I substitute that, x n by 2 plus L is going to be equal to g of L. So g of n by 2 plus L is same as g of L because of the periodicity. Gk and hk are periodic with period n by 2. Plus e to the power minus j twice pi over n times k, which is n by 2, times e to the power minus j twice pi over n times L. I am skipping a step, but essentially e to the power minus j twice pi over n times, substitute k equal to n by 2 plus L. So this is n by 2, this is L. And in this example, n cancelled out, 2 cancelled out, and that's e to the power minus pi j pi. So that becomes equal to g of L, and this quantity is minus 1. E to the power minus j pi is minus 1, minus e to the power minus j twice pi over n L HL. So for x n by 2 plus L, that's what we get. Okay. And then for XL, we have GL plus e to the power minus j twice pi over n L HL. So for any L in that range 0 to n by 2 minus 1, if I just replace k by L in this equation here, XL equal to that. Xn by 2 plus L equal to that. And what does that say? If I take these two equations together, and then it says that I have the n by 2 point DFT Okay, so if I have the even DFTs and the odd DFTs, so this says that if I want to compute these two quantities from the XL and XN by 2 plus L, it says that take the H quantity, HL, this quantity, multiply by e to the power minus j twice pi over n L, and then take a 2-point butterfly of that, and this becomes then XL, and this becomes XN by 2 plus L. So does that make sense? So XL is GL plus e to power minus that times HL. So this quantity here is GL, this quantity here is HL times e to the power minus j twice pi over NL, and this plus that is XL, and XN by 2 plus L is that quantity minus that quantity. So that's this minus that, and this thing again is called one of our simple units, which is the butterfly unit. Okay, so that's our butterfly unit, and this is called the twiddle factor. So anytime you multiply edges by this complex exponentials, that's the twiddle factor. So in fact, I can complete this diagram, but G0 and H0 can be combined to get x0 xn by 2, and finally, well, I could show you the final one. So the final one is going to be the twiddle factor is going to be e to the power minus j twice pi over n times n by 2 minus 1. So that's the last L. So L, this L changes from 0 to n by 2 minus 1. And then do the 2-point butterfly of that, and then you get xn by 2 minus 1 and xn minus 1. So without drawing a lot more, I can just show you from your textbook what the diagrams look like. So what I have just shown you is this figure 9.4. Figure 9.4 is showing, well, actually that's I have not shown you 9.4. In fact, well, okay, let me tell you what is going on. I mean, so in this figure 9.4, we are computing the G and H, but these twiddle factors are not separated into butterflies. So if you take some factor common, then I have shown you a simplified version of that. Okay, anyway, that's fine. So how does the divide and conquer continue? So the divide and conquer continues in a way that the n by 2 point, each n by 2 point can be described as 2n by 4 point and merge, and then the whole n point, this was the n by 2 point, another n by 2 point and merge, each n by 2 point is 2n by 4 point and merge, 2n by 4 point and merge, and all merge. So that's okay, so that's kind of what you see at the end. So if you go through that, ultimately we have everything expressed in terms of 2-point butterfly. So remember the decimation in time. So the first step, this is 8-point DFT. In the very first step, we computed all the even x 0, 4, 2, 6. So these are 0, 4, 2, 6. These are odd 1, 3, 5, 7. Now we applied for 0, 4, 2, 6. Do it again. So take the even parts of 0, 4, 2, 6. So you take 0. Think about 0, 4, 0, 2, 4, 6 as A, B, C, D. Then you take A and C, decimate again. And then the odd part of that is B and D. So that's the even of the even parts, odd of the even parts, even of the odd parts, and odd of the odd parts. Okay, so these are the twiddle factors. There is some simplification going on, and these are the butterflies. So if you count in each, so 8-point DFT at the end, we'll have log 8 to base 2. Divide and conquer means each time, how many times, if you solve a problem of size n, using 2 n by 2 point, how many stages do you need? Well, you need to do that in log n to base 2 times. Okay, so if we have 8-point, then we have log 8 to base 2. So this is first stage of the butterfly, first stage of the FFT, second stage, third stage, and the first, each of these is a butterfly 1 minus 1. And here, so total number of butterflies in each stage is n by 2. So this is 8 points. So there are 4 butterflies here, 4 butterflies here, 4 butterflies here, and these inside, in between the butterflies, there are these twiddle factors. So that's called decimation in time, because in the time domain, the signal samples are input in a decimated manner. The outputs in this flow graph are computed in place manner. 0, 1, 2, 3, 4. These are sequential in frequency domain, decimated in time domain, called decimation in time. The dual approach of that is to compute the decimation in frequency, where in time domain the signals can be in order. So these could be 0, 1, 2, 3, 4, etc. And these would be in the decimated order, in the decimation in frequency. So they would be 0, 4, 2, 6, and these indices come here, these indices come here, and that's called decimated in frequency. Decimated in time means frequency domain in sequential order. Decimated in frequency means time domain in sequential order. Okay, so you will have a lot of fun with these kinds of things in your homework. So let me see. So one other thing before I go to decimation and frequency, you will notice that some of you might have heard of this so-called bit reversed index. So, okay, let me explain what that is. So if we take in the decimation in time algorithm, the these indices are 0 to 7. So if you write this down in binary form, so these would be 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay, so those are the indices in binary format. If you reverse these indices, bit reverse these indices, then these, so just reverse them, 0, 0, 0, 0, 0, 1 became 1, 0, 0, 0, 1, 0 stays the same, 0, 1, 1, reverse 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. So these inputs are in bit reversed index, and so these are going to be 0, 4. You take the decimal versions of these binary representations, 2, 6, 1, 5, 3, and 7. So the indices of the and decimation and frequency will just be different, the reverse process. So the indices will be in bit reverse domain from input to output. And so just because a lot of computers have to compute FFT and store them in memories, this bit reverse is built into many instruction sets. If you are doing a computer architecture class and learning more about instruction sets and how they are designed, well, the instruction sets are designed to compute. Instructions are decoded and they go to execute units. Execute units have to have the hardware to do these operations. Okay, so we won't get into more of those things, although they are all fun things to talk about. Okay, any questions about decimation in time? Okay, so let me talk about decimation in frequency. So decimation in frequency, DIF. So the steps are a little different. So in the time domain, so when I computed decimation in time, we took the we took the computation of xk, and then we wrote that down as two sums, where the first sum was decimated in time for the even part and second for the odd part. We are not going to do that here. So the process here is slightly different, although similar. So first, the idea here is to compute the even DFTs. So compute even DFTs. So instead of thinking about even time domain samples and odd time domain samples, think about computing the DFTs separately. So we will substitute k is equal to 2r in xk to compute the even DFTs, and k is equal to 2r plus 1 to compute the odd DFTs. We are running out of this notebook, and let me see where the extra notebook should be somewhere. Okay. So they used to be here. Well, maybe our staff has to bring us a new notebook. Okay, so the first step, xk, which is summed over all n, xn, thank you, e to the power minus j twice pi over n, kn. So for k equal to 2r, so we are computing now the even DFTs. So x 2r, so replace x by 2r. So x 2r is equal to x n e to the power minus j twice pi over n. I have replaced k by 2r times n. N is equal to 0 to n minus 1. So all we have done is really replace k by 2r. I mean, that's k is equal to 2r and k equal to 2r. All right. Okay. So now we are going to again write this as two sums, but in this case we are going to write that as n equal to 0 to n minus 1, sorry, n by 2 minus 1. So we will take the instead of, so the two time domain sums, so these are decimated, but the time domain sums instead of decimated, they are in order. So the first sum is first n by 2 samples, the next sum is next n by 2 samples in the time domain. So xn e to the power minus j twice pi over n 2r n plus n is equal to n by 2 to n minus 1 xn e to the power minus j 2 pi over n 2r n. So I have not changed anything. All I have done is replace them as two sums. The first sum with index n equal to 0 to n by 2 minus 1 and second n to n by 2 minus n minus 1. Okay, so so in order to bring that index n prime equal to 0 to n by 2 minus 1, so we replace n prime is equal to n minus n by 2. So we do a summing change, and n equal to n by 2 became n prime equal to 0, n equal to n by 2 minus 1 became n prime equal to n by 2 minus 1. If we do that, and that says n is equal to n prime plus n by 2. Okay, and then e to the power minus j twice pi over n 2r n is going to be equal to e to the power minus j twice pi over n 2r n replaced by n prime plus n by 2. Again x to power a plus b, x to power a times x to power b. So that's e to power minus j twice pi over n 2r times n prime times e to the power minus j twice pi over n times 2r times n by 2. So multiply those into two parts, and then the 2 cancelled out, n cancelled out. And what do you see here? This, what is the value of this quantity? E to the power minus j 2 pi r is 1. That's a complex exponential which is periodic with period twice pi. So that's same as e to power j 0, which is 1. Okay, so now substitute this back here. So we get so we now get that is equal to, so x 2r is equal to n equal to 0 to n by 2 minus 1 xn plus, okay, I should make one more change. So n is equal to n prime, so this quantity here, okay, this quantity, so this is going to be n prime plus n by 2. So let me not skip a step, let me just continue and then we will write down. So this was, let's leave it as it was, e to the power minus j twice pi over n 2r n plus summed over n prime equal to 0 to n by 2 minus 1 x n is n prime plus n by 2 times e to the power minus j twice pi over n 2r n prime. The other quantity became 1, so it doesn't matter. Now n prime is a dummy variable, so n prime we can put it back as n. Just put it back as n, it doesn't matter. N prime is a dummy variable. So these two together then can be written as n equal to 0 to n by 2 minus 1 xn plus xn plus n by 2 whole inside a bracket times e to the power minus j twice pi over n Rn, and that 2r can be n by 2. So think about it. So these two terms, e to the power that, e to the power that are same. So I take these two sums, put them into one sum with that taken outside a bracket, and that quantity 2r, 2 comes and becomes part of n by 2. So what do you see this quantity is? Any volunteers? So this is equal to the n by 2 point DFT of xn plus n by 2. So that suggests that the even samples of DFT are simply n by 2 point DFTs of the n by 2 point samples obtained by this quantity. So if you take x0 plus xn by 2, x1 plus xn by 2 plus 1, and all the way to xn by 2 minus 1 and plus xn minus 1. So you take these n by n minus n point samples and then compute its DFT, and that becomes the even DFT samples of xk. Any questions about that? Well, we are at least a half done. We are not completely done because we have now expressed the half of the, so we are trying to compute the n point DFT. So we are trying to express them as a 2n by 2 point DFTs. Clearly the even point DFTs are 1n by 2 point DFT. So what do you see as the major difference here? The major difference is the so-called the post-processing. So the merging or post-processing. Compute n by 2 point DFTs, sum-to-real factors and then merging. So now instead of merging, so the last step here is the n by 2 point DFTs, but there is some pre-processing going on. So in decimation in time, you do post-processing of the DFTs. In the decimation in frequency, you do pre-processing of the time domain samples and then compute n by 2 point DFT. And that becomes more clearer as I compute the next one, x2r plus 1. So we start with the same equation here and substitute k equal to 2r plus 1. So x 2r plus 1 is equal to summed over. Let me just skip a step and write this as two sums. So n equal to 0 by 2, 0 to n by 2 minus 1, x n e to the power minus j twice pi over n, k replaced by 2r plus 1 times n, plus n equal to n by 2 to n minus 1 xn e to the power minus j twice pi over n times 2r plus 1 times n. Okay, so that's kind of the k replaced by 2r plus 1 and the all sum described as two independent sums for first n by 2 time domain samples and the last n by 2 time domain samples. We go through the same process. We go through exactly same process where we replace n minus n by 2. So n minus n by 2 is equal to n prime. So n is equal to n prime plus n by 2, and that becomes 0 to n by 2 minus 1 and this becomes n becomes n prime plus n by 2, and this n becomes n prime plus n by 2. And let's stop there and try to compute this whole thing and see what's going on. Okay, so first of all, how many of you see that this quantity, if I write that down, becomes e to the power minus j twice pi over n 2r plus 1 times n prime times e to the power minus j twice pi over n 2r plus 1 times n by 2. So we have just taken this n prime plus n by 2, write that as two terms, n prime here and n by 2 here. Okay, so now n cancelled out, 2 cancelled out. So what do we get now? So this becomes equal to e to the power minus j pi 2r plus 1. Anybody knows the value of this quantity? How many say minus 1? Too many. How many say plus 1? Okay. This is an odd multiple of pi. 2r plus 1 is an odd. E to power minus j pi, e to power minus j 3 pi, 5 pi, minus or plus, doesn't matter. And that's minus 1. Okay. So the even multiple of twice pi is plus 1. Odd multiple. This is 2r plus 1. This is an odd number. So that's equal to minus 1. Okay. So that means, so now the n prime is a dummy index. We bring that back as n. So this becomes n. Now that n by 2 can be thrown out only with a negative sign. So put a negative sign here, and then this term e to power minus j 2 pi over n 2r plus 1 here, and the n prime is same as n. These two are common. I can take them outside a bracket and replace the two independent sums as one sum. Same thing as before. Okay, so if we do that, so then we get x 2r plus 1 is equal to summed over n equal to 0 to n by 2 minus 1 xn. Remember that n by 2 became minus xn plus n by 2 times e to the power minus j twice pi over n times n, all times e to the power minus j twice pi over n to Rn, and the 2 comes to n by 2, and that becomes Rn. So this is the n by 2 point DFT of xn minus xn plus n by 2, all multiplied by a twiddle factor e to the power minus j twice pi over nn. And that's the part of the pre-processing step. So the pre-processing step has to be taken care of. So that says that if I have some xn and some xn plus n by 2, so first you compute a 2-point butterfly of that. This is xn plus n by 2, and this is xn minus n by 2, and this is multiplied by a twiddle factor e to the power minus j twice pi over n times n, and here n changes from 0 to n by 2. So you have 0 to n by 2 minus 1. So you have n by 2 samples like that, other n by 2 samples like that, and then the whole thing here goes through this pre-processing, and at the end of pre-processing we have these samples here, n by 2 of them, and these samples here, n by 2 of them, and then compute n by 2 point DFT of all these, and then compute n by 2 point DFT of all these, and these become x2r, the even samples, and these become x2r plus 1, the odd samples. Okay. So that's essentially it about the decimation in frequency. We compute the DIF, and you basically keep doing the same thing, express this in terms of 2n by 4 point, express this in terms of 2n by 4 point. So we will have this log n stages at the end of butterflies and twiddle factors. So very similar, but slightly different derived in slightly different ways, but still there is a tremendous amount of similarity among all these. Any questions about the basic ideas of so-called Cooley-Tukey FFT algorithms? By the way, Cooley went on to receive the IEEE Kilby Medal, Jack Kilby Medal, for signal processing, for inventing the FFT. Unfortunately, I believe Tukey was dead and he couldn't receive the award. I think it's not the other way around, I think, although we can find that out easily. Talking about which, how many of you have heard of Jack Kilby? A few of you. Well, Kilby invented, believe it or not, the first transistor, first integrated circuit. So transistors, of course, were invented by Bardeen, Bratton, and Shockley. The first integrated circuit was invented by Mr. Kilby, who worked at Texas Instruments. So Kilby did his undergraduate in electrical engineering at University of Wisconsin, then master's in Urbana, and worked at Texas Instruments all his life, and was granted the first patent of so-called invention of the integrated circuit. And I assume in this class there is no single one of you that doesn't know what integrated circuit is. So that's the Kilby Medal was established to honor signal processing contributions. And some of you might know Jack Kilby went on to receive the Nobel Prize in physics for the invention of the integrated circuit. Okay, so let me go to our slides and see how much content we have covered, and then we can see if there is more to cover. Okay, so let's quickly take a look. So we talked about computing the 2-point DFTs, A plus B, A minus B, and we briefly started talking about the decimation in time, where there are some small mistakes. The cap n on the top right should be small n, but anyway. So but anyway, so that's kind of decimation in frequency. Replace k by 2r and k by 2r plus 1. This is just what I was trying to complete. Okay, so we want to talk briefly about some matrix representations of the same thing. So for a 4-point DFT, if we are given x0, x1, x2, x3, and you can show from the definition that we can get the 4-point DFT matrix as shown here. So if we call that DFT matrix V, and we are computing cap x is equal to V times the time domain vector small x, and you will notice that the second column, second row and second column are same, third row and third column. So this V is a symmetric matrix, and that means V is same as its V transpose. So whether you implement V or its transpose, they are essentially the same thing, because V is its own transpose. So let me write down this V matrix in a general form, and then maybe it will become clearer that So the so-called DFT matrix V, which comes from our definition, right? So that's our definition, xk. So if you substitute, okay, so this is, okay, cap x is equal to V times small x. And cap x is x0 through xn minus 1. Okay. And this is small x0 through xn minus 1. So, so imagine that this is here and this V matrix times x0 through xn minus 1. So the first elements of x0 substitute k equal to 0, so we get all ones. Next row, x1, we are computing x1, substitute k equal to 1. So x0 times substitute n equal to 0, you get 1. In the next one, we get e to the power. As you read the book, the so-called Tweedle factors, so the notation w, e to the power minus j twice pi over n, is used as the notation for the book, and this is sometimes called wn. So, so in any event, so that's going to be e to the power minus j twice pi over n, and substitute n equal to 2 and k equal to 1, so that's w squared. So if this is w, so if that's w, then keep taking square of that, so w squared, w cube, etc. Okay, so the next one, 1, and what's the first element? Here k is equal to 2, n is equal to 1, so that's w squared, w fourth, w sixth, w eighth, etc. 1, w cube, w to the power 6, and so on, k equal to 3. So, so if you take this third row, 1, w squared, w to the power 4, 6, 8, and third column, they're all same. So V is same as its V transpose. So that means if I compute x is equal to V times x, or compute V transpose times x, they are computing same thing. V matrix is the same as its transpose. And believe it or not, we think about, if you think about this V as decimation in time and transpose that, and that V transpose you will get as the decimation in frequency. So you just start with the data path or the flow graph that computes decimation in time. So x0, for the example that I showed, x4, x2, x6, etc., and computes cap x0, 1, 2. So transpose means reverse the edges, the output edges become input, the input become output, traverse every edge. Every edge, if it was going left to right, you transpose that in the flow graph, make it right to left. So we could talk more about that, but that's kind of what transpose means. You transpose the decimation in time and you get back decimation in frequency. So we'll get back to some of those, but let's continue with these slides. I want to get back and talk more. Okay, so there is something called a permutation matrix. Those of you might have seen, how many of you have taken a class linear algebra like math 4242? Very useful if you are ever going to be doing signal processing. That's kind of, if you ever go to graduate school or work as a signal processing engineer in your life, yeah, this class and take, at least take 3025 probability stochastic processes and the linear algebra class, then I think you are ready to go to graduate school. And if you haven't taken those, you can still take them in graduate school. That's okay. Although if you do go to graduate school, you should, and if you do go to graduate school here, you should take the probability class, which is 5531, the graduate version of 3025. Okay. So P is a permutation matrix that has one entry in any row or column, that is 1. P is same as its transpose, PP transpose is identity P equal to P transpose equal to P inverse. Okay, that's okay. So one example of the P matrix is, so every row has only one. Every column has only one. So why do we need to use this P matrix to describe the FFT matrix formulation using permutation? Because anytime I do a decimation, I use a permutation on the input elements. So if I think about P times in order samples x0, x1, x2, x3, and I make them decimated 0, 2, even samples followed by odd, and that can be obtained by that P matrix shown on top left. So finally, we can describe the DFT of the 4-point matrix that we had shown here. So this matrix here, 1, 1, 1, 1, 1 minus j minus 1j, etc. describe that as a product of a V4, and you can quickly recognize that V4 is nothing but butterfly operations. So this, whenever you see this 1, 1, 1, 1, 1 minus 1, they will do the butterfly. The D is the Tweedle factor matrix. So the three diagonals are 1. The last one is minus j, means only one Tweedle factor, which is just minus j. And V2 and permutation times x. And if you take the 8-point DFT that we just talked about, this is the 4-point DFT. 4-point decimation in time. If you look at the top diagram, 4-point decimation in time. Time domain samples are decimated 0, 2, 1, 3. Frequency domain in order 0, 1, 2, 3. And that's showing the two butterflies. That's the and then the minus j. That's what you saw, minus j. And finally the merge. So this matrix X, which is showing here as so the top diagram is actually showing V, which is from this equation V4, D, V2. So think about the first column as V4, next as D is the, and then V2 times okay, I probably am not saying that right. Yeah, so I'm not saying that right. So when you compute x is equal to V4 d V2 px, so start with x, then permute, then go to V2, then d, then V4. So in the top diagram, start with x, then permute. Permute matrix is not shown here. That's the output of the permute. And then use V2, these are V2, then diagonal V4. Okay. Take the transpose of that, then that becomes P. P transpose is same as P. V transpose is V. And V2 transpose is V2. V4 transpose is V2. D transpose is D. D is a diagonal matrix. So then we finally get that. And if you look at what we are showing on the bottom, so now we start with X in order. X in order. This is the V4 matrix, diagonal matrix, V2 matrix. And then I don't show that permutation, but if you permute, you get back to X in order. So this is actually obtained by transposing the decimation in time FFT. So what I'm trying to show you here is if you compute the decimation in time and transpose every edge by just reversing the edge, or in mathematical form transposing the matrix and implementing these like that. Either way, transposing the DIF gives you DIT and vice versa. Okay, so I think we are running out of time, but let me just make one remark, and then we'll make a couple of more remarks later on, but let me just make one remark and then we will stop. So if the signal xn is real, we talked about the fact that xk is x conjugate n minus k. So that means if the signal is real, you can compute only n by 2 samples. So for example, if n is equal to 8, there are many ways of computing the 8 samples. So in one approach, we can compute x0, x1, x2, x3, x4. And then I can compute the rest from transpose. So for example, x5, is going to be x conjugate 3, x6 is going to be x conjugate 2, and x7 is going to be x conjugate 1. So in your homework, you are to show some diagrams. Let me just take a very quick look. So we have one problem that is following from chapter 8, coming from a final exam question from last time. One homework problem from the book, and then a few problems for you to work about on your own. But if you look at the last problem, what I intend you to do here is assume the signal to be real and throw out the data paths that we don't need and compute only n by 2 plus 1 points so that the remaining parts are thrown out. So simplify or prune the FFT flow graph only to compute what we really need, such that we are not computing unnecessary components if the signal is real. So okay, I have handed out your midterms, those uncollected midterm exams. Please return them to me before you leave, and see you next class.